Good morning, everyone. Okay, I'm assuming you can hear me now. Sorry, I was just having my breakfast, and I didn't think everyone wanted to hear me chew. And I usually wait a couple minutes for people to stream in. Looks like we got about a dozen people, which is good. While we were waiting, there have been a few requests just to go over some of the solutions in the homework. I think that's great. Okay, so let's start off with number 11. Actually, before we jump into it, I just want to say that I've been reading the feedback. I really appreciate the feedback. There's been some really good suggestions. I think so far my favorite suggestion is that we need more Goose. I'll do what I can. I'll try to convince her to join more of the streams, but she's very busy. You have to understand that it's not like she just sits around and naps all day and kind of just sleeps and hangs out. She's got a very busy schedule, so I'll see if I can convince her to free up her agenda and make more time for us. But it's in her hands. Okay, so let's jump into. Oh yeah, one more thing before we get started. Tomorrow's a day off for you, not for me. So since report cards are coming up, we're gonna have the teachers are gonna spend Friday writing report cards. So that means I won't have a stream tomorrow. So you guys have the day off. Okay, so let's talk about number 11. So we're going to explain why this does not need an absolute value. Okay, so we have to understand that sometimes we do need an absolute value. So when do we need an absolute value? Okay, well, let's think about it. So let's say, okay, suppose we have the square root of x squared. Okay? Well, the thing about the square root of x squared is that x in this case can be anything. X there's no restrictions on x here, because if we had like -1 squared and we took the square root of it, that would be, well, the square root of, -1 squared is +1, and then the square root of 1 is just 1. But then we also have this, that +1 squared, if we take the square root of that, then that is also going to be the square root of just +1, and that's just 1, right? So the way we have to combat this is by saying that, well, in this case we just got what x was equal to. In this case we got the positive version of x, right? So the square root of x squared is +x. Now this question is saying, well, hold on a second. Why do we not need an absolute value symbol? So first of all, they're specifying that y is greater than 0, and they're doing that because if y was negative, then we'd be taking the square root of a negative number, and that's no good. So don't worry about the y. The question is really asking about x. Well, why don't we need an absolute value sign around this x? Well, it turns out it's actually not that complicated. So the idea is, so I'm gonna simplify this. So we've got x to the 4 times y, and this is going to be, well, it's going to be x squared, right, times y, right, and that's the idea. Well, the thing about x squared is it's already positive, right? There's no way that this could be negative. So this is definitely positive. We don't have to worry about the positive sign. Let's try it with a couple of numbers and see what happens. Like the idea here is that when it comes out of the brackets, it becomes positive, right? So we have to say, okay, well, we're going to take this -1 and turn it positive. The only way to do that is to put absolute value signs around it. Here, on the other hand, we've got x squared, and x squared makes it positive on its own. So we don't need the absolute value symbol because we already have the squared symbol, right? This squared symbol here makes it positive. So if we wanted to, you could have the absolute value of x squared, but that's redundant, right? Redundant means that it's extra information that is unnecessary, right? So so yeah, if you wanted to, you could put the absolute value symbol. It's not like that's wrong, but because you've got x squared here, the x squared is already positive, and so the absolute value symbols become redundant. So that's number 11. So I hope that answers your question. So if you still have any questions about it, feel free to reach out again. Okay, number 13. This one was also requested. So I've got the volume of a sphere. This is volume of a sphere. Okay, good. So this is the volume of a sphere. It's something that maybe you've seen before. You've probably seen it at some point. I hope you have. It's kind of like one of the more important formulas for you to sort of have in your tool belt. So 4/3 pi r cubed. That's the formula for the volume of a sphere. So let's just punch in a few values and see what happens. So let's say that let's say that r is equal. I'm just doing this just to sort of warm us up a little bit. So let's say that r is equal to 2. Let's say 2 centimeters. Okay. So the radius of a sphere is 2 centimeters. You can calculate the volume by saying that v is equal to 4/3 times pi times r cubed. So in this case, we'd have 2 cubed. And if you want to be very, very specific, you could actually say it's 2 centimeters cubed, and then you'd have your appropriate unit, right? You'd have centimeters cubed. So in this case, we'd have, well, 4/3, and I'm just going to say this is 3.14, and then 2 cubed is 8. So I've got 8 centimeters cubed, and I guess we can just do this. We're just going to multiply all these together. So 8 centimeters cubed, 8 cubic centimeters, and I guess we can plug that into a calculator really quick. I finally have my calculators handy. I left them at school for a little while, but I went to school the other day and picked some stuff up. So I got 4/3 times, and I'm just going to do 3.14, and then times 8, and that's equal to 33 point, I'm going to say it's close enough to 33.5, okay, centimeters cubed. And I'm going to put a little dot on top of the equal sign to indicate that I've done some rounding. Okay. So you can imagine that that as the radius changes, the volume changes as well. I mean, I guess that's kind of obvious, but if it's not obvious, I mean, here's a nice little sphere, right? You can kind of imagine sort of a three-dimensional looking sphere like this. Here's the center of the sphere right here. And then the radius of the sphere is the distance between the, and maybe I can even try to make it look a little more three-dimensional. Okay, so here's a point on the actual surface of the sphere, and the radius is that line from the center all the way to the surface. So as the radius expands, the volume changes as well. But the thing about it is that it doesn't change in kind of a linear fashion. So consider this. I'm going to do a little more of a straightforward example, and then we'll see what happens here. So consider, let's consider kind of an easier concept than the volume of a sphere. Let's consider the area of a square. Okay? And in fact, this is a great example, particularly the one about the sphere, because it's square, because it has huge implications in the history of math. For a very long time, mathematicians couldn't I mean, and I'm talking about a very long time ago. Like we're talking like we're talking like 300 or 400 BC here, like ancient Greek times. They weren't able to double the area of a square. They didn't know how to do it. And in fact, and this sounds crazy, but the very first mathematical martyr, that is someone who was murdered for the sake of what they believed in. So they were advocating for something and they died as a result. The very first mathematical martyr died over this very concept, so doubling the square. And if you want to look into that a little bit further, you can look up Pythagoras. And in fact, this guy who we love so much, Pythagoras, it was him who murdered the person who felt like you could double the area of a square. So I'm kind of blurring the lines. It's not quite as direct as that, but you should look into it if you're interested. It's quite a cool story. Apparently he pushed someone overboard because someone thought that the square root of 2 was irrational, that you couldn't write it as a ratio. So yeah, this has everything to do with the square root of 2. So let's anyway, back to this. So let's say we have the area of a square. And let's say that area, so I've got S times S, right? That's how you calculate. So the area is equal to S squared, right? So let's say that the area is A, right? So A is, so 2A, what happens to the side? So let's say I have an area that is twice as big. Now, it's kind of hard to imagine exactly what that looks like. So if I have something that's 2A, it's not like I double the sides, right? Like if this is 2S and this is 2S, well then the area here is going to be here. The area of this one is going to be well, it'll be 2S squared, which is going to be 4S squared, right? Which is, well, I know that the original area over here was S squared. So if I double the side length, I quadruple the area, right? So it's not quite as simple as, so if I said that, and you can see that right off the hop, right? Because this is 1 block and this is 4 blocks, even though I doubled one side. So if I double the side length, I quadruple the area. So that raises the question, how do you just double the area? Like, what does that look like? And it turns out it's not straightforward, okay? So let's say we want to say, okay, I want something that has twice the area of this one, of this first one here. So let's say I want to double this area. How do I double this area? Well, I'm going to say that 2A twice the area, so that's going to be blank times blank. So we're trying to figure out what the side length is, and we're going to see what relationship that has to these S sides. Okay, so this is of course going to be x squared. So x squared is 2A, or in other words, x is equal to the square root of 2 times A. Okay, well what does that have to do with S? Well, if we go back over here, S is equal to the square root of A. So it turns out that x is equal to the square root of 2 times the square root of A, right? That's coming from that equation. But the square root of A is S, so this is the square root of 2 times S. Okay, so what am I saying here? That if I want to double the area, of a square, what I do to the side length is I multiply that side length by the square root of 2. And the square root of 2, going back to history, the square root of 2 was not an obvious value. Like like we kind of take that for granted, right? We can punch into our calculator and blah blah blah. It's like 1.414 blah blah blah. You know, you can see right away that the square root of 2 exists and it has a decimal expansion. And you also have a math teacher who has told you, oh, my stream okay? Okay. You also have a math teacher who's told you that the square root of 2 is irrational, right? And we kind of know about irrational numbers. But you can imagine in history, if no one told you that, would you know that the square root of 2 is irrational? Would you know that like how to calculate it? Would you know that it's 1.41 if you didn't have a calculator? Like, these things are not obvious. You, like, it's really hard to imagine a point in history when we didn't know that. So you can imagine if no one has told you these things, it would be very difficult to figure that out for yourself. So the square root of 2 is important here, because if I want to double, so if I want to double the area of a square, to double the area of a square, I need to multiply the side length by the square root of 2. Okay, that's what I have to do. I have to multiply the side length by the square root of 2, and when I do that, the area doubles. And it turns out with a ruler and compass, which is how they used to always do mathematics, is it wasn't with algebra, it wasn't with numbers that we write down, like with numerals and variables and things like that. The way mathematics used to be done by the ancient Greeks was with a ruler and compass. So that's, I don't think I have one here, but I think you've seen those. It's like how you make a perfect circle. There's this great book. I've got it right here. I did have it right here. Oh, I think, you know what? I may have taken it to school. I think I did. I've got this other version of it. This is good. Euclid's Elements, right here. Euclid's Elements. That this is how they used to do math. So this is a, and this isn't actually the best version. This version is more intended for people who like ancient history. This version is not so much intended for mathematicians. Mathematicians like diagrams and drawings and stuff, where this one is more of an investigation into the language, and I believe that there's some of the original ancient Greek in this version. So I wish I could find some cool diagrams for you. I mean, this is what ancient textbooks used to look like in ancient Greece. Is that they had, it was all about diagrams and circles and straight lines and things like that. Yeah, this version has like almost no diagrams, which is ridiculous. Here we go. Here we go. Oh, they're just later on. Okay, I get it. So this is what ancient math used to look like. Is that you do everything, you'd be making circles and straight lines and things like that. I guess you can't really see that. So it'd be about straight lines and circles and cool stuff like that. So it turns out that doubling a square, like doubling the area of a square with a ruler and compass is impossible. You can't do it. So there's no way of doing it. So the ancient Greeks thought that you just couldn't. There's no possible way. Now with algebra, thank you to thanks to history and developments in algebra, in particular in the Middle East and Arabic-speaking countries, and my history is a little bit shaky around that, but a fellow named Al-Khwarizmi invented algebra, and then boom, the whole mathematical world blew up, and then now we have algebra, and we can say, the square root of 2 is exactly what you need, and now we've got numbers and numerals and things to represent these things, instead of doing like a little circle and trying to like find the area by taking this line and copying it over here and seeing if you can make like a square that's twice the area. You can't do that with a ruler and compass. You can do it with algebra. So we're going to do this with algebra. And I know that I'm getting a little carried away here, but this stuff gets me really excited. I really like this stuff. So what happens to the volume, or what happens to the radius when the volume is multiplied by 8? So let's say that I've got let's say I've got a volume. So I'm going to call this volume 1. So this is going to be our initial volume of a sphere. Okay, and that's going to be 4/3 pi r cubed, and I'm going to call that r1. Okay, because that's my initial radius. So here's my sphere, and it has volume v1. Okay, it has volume v1. So that means that the radius here, the radius is r1. Okay, so we want to know if I had a sphere that was exactly 8 times the size in volume, how much bigger would the radius be? Okay, like so if we took the volume and increased that by 8, so you can kind of imagine like maybe you've got this kind of funny basketball that you're blowing up, and as you blow it up, and I know this doesn't happen in real life, but you can imagine a basketball that as you blow it up, it gets bigger and bigger and bigger, right? And let's say you put like 10 cubic centimeters into your volume, and that's what this one over here is. Let's say that this is like 10 cubic centimeters, right? And then maybe you keep blowing it up, and then now all of a sudden you've got 80 cubic centimeters, and you've got this really, really big one, right? Is the radius just 8 times the size? Is the radius like 8 times the size of the original one, or is it some other factor? Well, let's get to the bottom of it. So let's say that V2, my second volume, and this over here would be R2. So my second volume is going to be 8 times the size. It's going to be 8 times the size of my first volume. It's going to be 8V1. Okay, so let's see if we can figure out what the radius is going to be. So I know that so what I want to do is I want to say, okay, so my second volume, or sort of my original radius, or sorry, my new radius, let's write a new equation saying, okay, so I've got 8 times v1, that's my new volume. That's going to be equal to 4/3 pi r2 cubed. Okay, so our second volume, and what we want to do is we want to figure out how is this related to our original radius. Well, what I'm going to do is I'm going to isolate r. Okay, I'm going to isolate r. So basically, what I'm going to do is, really, I think I might be kind of making this overkill. I mean, the idea here is that this is the only variable. You know, I'm going to take this in a different direction. This is the only variable. Okay, only variable. Okay. So yeah, I'm just gonna go straight to the answer here, because I think we could attack with algebra all day, and you might not really fully understand what it is. So I'm just gonna tell you how to think about this one. This is our only variable, and it is growing in a cubic way, right? So it's not like if I double the size of the radius, I get double the volume. Okay. So if let's say that I've got 4/3 pi r cubed, and let's say that r is initially like 2, and we've already calculated this one. It'd be 33.5. That's 33.5 cubic units. So if we're dealing with centimeters, then it'd be cubic centimeters. What if I doubled what if I doubled the radius? Let's see what would happen if I doubled the radius. So I've got 4/3 pi times 4 cubed, and let's figure out what that is. So I've got 4/3 times 3.14 times 4 cubed, and that is 267.9. I'll just call that 0.9, and I'm gonna have rounded, and that's rounded as well, and that's gonna be centimeters cubed. Okay, and okay, now what we should do, let's figure out how much, like, clearly if we've doubled the radius, how much bigger did it get? Well, let's see about that. Well, I'm gonna say, okay, well, 267.9 divided by 33.5, that's equal to, well, it's approximately equal to 8. It's approximately equal to 8. Yeah. Is it a coincidence that the cube root of 8 is 2? No, it is not a coincidence. Definitely not a coincidence. So this is approximately 8 times larger. So if I double the radius, then what happens is the volume gets multiplied by 8. So that's kind of the quick answer is that when you multiply the volume by 8, what's happening is the radius is getting bigger by a factor of 2. Okay, and you can kind of see this by saying, okay, if I've got 4/3 pi r cubed, and if I were to double r, what would happen to the whole volume? Well, I would have 4/3 pi times, well, 2 cubed is 8 times r cubed, right? So when we double that volume, when we double the radius, the volume gets multiplied by a factor of 8. So that's what happens. I hope that answers your question. And I'm sorry if you found the history bit a little bit boring, but I think it's really interesting. Okay, I want to do just one more question, but we're going to do it in a slightly different way. I'm going to give you about 3 to 4 minutes to try this one on your own, if I can find it. Where is it? Oh, no, not there. Here it is. Okay, I want you to try this problem on your own. I'm going to give you, maybe I'll give you 5 minutes. I'll give you 5 minutes, and then I'm going to cut you off, and, excuse me, and then we'll do it together. So I've got the square root of 2x plus 5, square root of 2x plus 5, minus the square root of x minus 1 equals 2. Okay, so there's my equation, and yeah, so I'm gonna get you to solve that one for me, and I'm gonna come back in 5 minutes. I'm gonna set a little timer here. Here we go. Here's a timer. I wonder if you can actually see that. Okay, yeah, you can see that. So the timer is gonna be set for 5 minutes, and when that timer goes off, I'll come back and I'll see how you guys are doing. Okay, here we go. Okay, let's do this problem. Yeah, so I'd be hesitant to try to do this question in your head, because there's more to it than you might think. So I'm gonna start off by isolating one of the radicals. Okay, so I'm gonna start off by isolating the one on the left here, and I'm gonna do that just so that everything becomes positive, because the second one currently is negative. So if I move it over to the other side, then what I'm gonna get is root, and I'm gonna make this a little bit bigger. I'm gonna get root 2x plus 5 equals 2 plus root x minus 1. Okay, now that that one's isolated, I can square both sides of the equation. And you know, I really should be talking about restrictions first, but we'll kind of ignore the restrictions for now. But let's just say that we figured out the restrictions. Later on, when we go back, we'll double check our solutions and make sure that they're consistent with the restrictions. But assuming that we've done all the restrictions and everything works out, I'm going to get that 2x plus 5 is equal to, and I'm just going to square this directly. I'm going to go straight to the square. So I've got, well, 2 squared is 4. Then I'm going to have 2 times root x minus 1 times 2. So in other words, 4 root x minus 1. Okay, and if you're not sure how I did that, I'd suggest doing a little more practice, because this sort of thing we have to do a lot of. So if you don't see how I got that, do a little more of the homework. You got to spend a little more time practicing these, because this does come up quite a bit. So I've done that. Now I'm going to clean it up. I'm going to bring the other stuff to the other side. So I'm going to bring the 4 and the negative 1 to the other side. So in other words, like this 4 and this negative 1 become 3, positive 3. When I bring it to the other side, it becomes negative 3. And I'll add that to the 5, which gives me 2. So we've got 2x plus 2 plus 2. And I should actually worry about the x's now. So I'm going to bring the x to the other side as well. So I've got 2x minus x, which is just positive x. So I've got x plus 2 on this side. And this is equal to 4 times root x minus 1. Okay, that looks good. Now the radical on the right has been isolated. So I'm going to square both sides again. So I'm going to do this. I'm going to say this squared and then this squared. So I'm going to get, on the left I'll get x squared plus 4x plus 4 equals, and on the right I've got 16 times x minus 1. And now we're just going to sort of clean it up and solve the quadratic and call it a day. So I've got x squared plus 4x plus 4 equals 16x minus 16. I'm going to bring everything over to the other side. So, excuse me. I'm going to have x squared. Well, when I take the 16 to the left, I subtract 16. So 4x minus 16x is negative 12x. And then when I take this negative 16 to the other side, I'm going to add it. So I get 20. And that's all equal to 0. And now I can factor this. I can factor it. So I'm thinking negative 10 and negative 2. That's probably what I can get. So x minus 10 and x minus 2 equals 0. Okay, that looks good. And in order for either of these to be equal to 0, I will get x equals 10 or x equals 2. And so I kind of cheated on this one a little bit because I forgot to check the restrictions first. So what are the restrictions? I'm going to quickly do the restrictions now. So the restrictions are that 2x plus 5 must be greater than or equal to 0. So in other words, x must be greater than or equal to negative 5 halves. And then the other restriction is that x minus 1 must be greater than or equal to 0, or in other words, x must be greater than or equal to 1. And if I combine these two together, really what this is saying is that x must be greater than or equal to 1. Okay, x must be greater than or equal to 1. So, both of these answers are greater than or equal to 1, so I'm not breaking any of my restrictions, but we still have to check our original answer. Okay, we still have to check our original, or I shouldn't say original answer, I should say we have to check our answers in the original equation. So let's check both of those answers and see what we get. So I'm just going to copy this so I don't have to keep scrolling back and forth. I'm going to go copy and then paste. Okay, and supposedly our solutions are, so we're going to check, check x equals 10 and x equals 2. Awfully sorry about that sound. Oh my gosh. They're taking down the tree in my front yard. Holy smokes, that's crazy. Let me show this to you. This is actually really exciting. Here. Where's my camera? Where'd my camera go? Here it is. Oh, I'm all tethered. Look at this. Isn't that exciting? Yikes. Holy smokes. I think they're doing this because of the ice storm. They've taken down like quite a few trees in this area, which is really sad because, you know, these are our trees. These are probably like, you know, 100-year-old trees. You can see down over here, they took that one down. Sorry for the distraction. It's just hard to concentrate when this sort of stuff is happening right in front of you. Yikes. Maybe later I'll show you the video I filmed of, I'll show you the video that I filmed of the tree falling down. Is actually really exciting. Well, I mean, it's quarantine exciting, right? I mean, it's, you know, if this was regular life, I probably would be like pretty bored by it, but like this seems very exciting to me. I don't know. Okay, so let's check our answers. So let's check x equals 10. So if x equals 10, we've got 2 times 10 plus 5 minus 10 minus 1 equals 2, and those are square roots, of course. So this is going to be 25. Square root of 25 minus the square root of 9 equals 2. So 5 minus 3 equals 2. Yeah, 2 equals 2 works. Okay, let's try x equals 2. So I've got root 2 times 2 plus 5 minus 2 minus 1 square root equals 2. Let's see. So this is 2 times 2. Oh, that's plus 5 rather. So that's, I've got 4 plus 5 is 9 root. So I've got root 9 minus root 1 equals 2. That's 3 minus 1 equals 2. Yeah, 2 equals 2. We're good. This is awesome. So that means we have 2 solutions. So I don't know if you remember the crazy example from yesterday. It was this crazy one where it took like 2 full pages and a whole bunch of explanations and yada yada yada, and there was no solutions. This one over here has 2 solutions. Imagine that. We've got 2 solutions. So let's head over to Desmos, and I'm gonna punch these 2 equations in, or these 2 expressions in, and we'll see what it means that when we say that it has 2 solutions. So I've got, okay, I'm gonna have to punch my keyboard into here. Okay, here we go. Come on. Oh, you know what I can do? Actually, I'm gonna put that back. And I'm going to do this. Aha, yeah, now I've got a mouse and keyboard. The new version of iPad OS lets you use a mouse, which is really fun and exciting. It's like having a little computer. Okay, so I've got the square root of 2x plus 5, 2x plus 5. Okay, and I don't know why there's brackets there. I'll get rid of those brackets. Not that they really do anything. 2x plus 5. Okay, and then I'm subtracting square root of x minus 1. X minus 1. Okay, good. And so that's one side of the equation. The other side of the equation is 2. And I guess what I should say is that this one is, if we're going to actually graph this, this is going to be y equals, and this is going to be y equals. So I've got two solutions here because I've got 2 points of intersection. I've got the point 2, 2, and I've got the point 10, 2. Imagine that. Because when y is equal to 2, there are 2 places where that happens in the expression of 2x plus 5 minus or root 2x plus 5 minus root x minus 1. So graphically, you can see that these two equations intersect, or these two expressions intersect. And if we wanted to, if we really wanted to, what we could do is we could cut that out, and let's do 2 plus square root of x minus 1. Okay, that's another place where they intersect. So basically what I did was I graphed this equation. This is kind of the equation that I think is actually the equation that we're concerned with. Is this one here, and when we graph it, you can see that there's one intersection at 10, 5 and at 2, 3. So still, even when x is equal to 2 and x is equal to 10, we still get those same intersection points. So there's a lot of different ways of interpreting these. I like this one because these graphs, these kind of like these arches, which we should talk about soon, is the graph of these radical functions. The graph of this is basically like it's a parabola on its side, right? Because it's the inverse of a parabola. It's the inverse of the square. Oh yeah, I noticed that they did the same at your house. Yeah, a lot of my students, because I keep talking about the trees being cut down, and a lot of my students are saying that the trees have been cut down by their house. Anyway, so yeah, these two radical graphs, they intersect each other twice. And I just had to show you my other cat, Kima, who doesn't quite get the same airtime as Goose, but you can tell she's quite entertained by this stuff. Kima's the older cat of the two. She's more wise and more learned and a little more refined in her tastes. But yeah, she's a little more camera shy, I think. So she hasn't been saying hi as much. But she's a very beautiful cat. Love her very much. Yeah, this is her entertainment. This is her Netflix. So she's quite entertained by all these trees falling down. Right, Kima? Hey, sweetie, show me your face. There you are. Okay. So yeah, I think we're gonna end it there. I'm gonna yeah, sign out in just about a minute. So a couple things. I think I already mentioned this, but no school tomorrow. Tomorrow is a PED day, so I'm going to be busy writing your report cards. Yeah, I think that's it. If you haven't filled out the feedback form, please do so whenever you can. I'd love to hear about what you think about the online learning, and I'd love to hear some of your suggestions. I've been reading some of the suggestions already, and I'll try to take those into account as much as I can. In particular, the one that I think that, I mean, I'd love to hear from about all of the questions I asked, but the one that I think you might want to think about the most is about the final exam. Like, what do we want to do for a final exam? Do we want a final exam? Maybe you want that. Do you want to do something in lieu of that? Do you want to do some kind of research project? Let me know, and I'll work around that. Okay. So I'm gonna sign out now, and have a good weekend. Oh, my mouse is not connected to my computer anymore. Yeah. So have a good weekend. Come on. Have a good weekend, and I will talk to you guys on Monday. And yeah. Oh yeah. Right. One more thing. Homework. I'm sorry. One more thing. Homework. Right. So for some reason, when I compiled that homework sheet for you guys, the equations bit. And look at this. I think I just lost a bunch of viewers because I said goodbye. That's annoying. Not that anyone did anything wrong. I pretty much said goodbye. But if you're still here, stick around for just one more minute. I have to talk about homework. When I initially compiled that homework, I forgot to include stuff on radical equations. So I'm going to include that. I'm just going to update that same PDF. So if you've printed that PDF, you may have to print an extra page at the end of it. Or I guess it would be in the middle because there's still the solutions underneath it. So if you've been printing it out, just print out that one extra page with the radical equations. It'll just be 2 or 3 more questions. And I will make a list of homework problems for you to do over the weekend if you want. Yeah, so until then, I'll see you on Monday. And stay tuned for the update on the homework. I'll put it on the webpage. Yeah, okay, take care. I'm actually going now, so goodbye.